Hello everyone, welcome to today's class. This is Teacher Simon taking you through AS Chemistry paper 9701 stroke 12 for May June 2025, and this is part 1 for questions 1 to 10. Question 1. Consider the following statements. Silicon dioxide has a higher melting point than sulfur dioxide. When we are talking about the melting points, we look at the structure and bonding, okay? And then after that, we talk about the strength of these intermolecular forces. Now, when you look at sulfur dioxide, it has the same structure as that of diamond. So you have silicon, and then it has this tetrahedral structure. So there is oxygen here, like that. And you know that each oxygen atom is supposed to have 2 bonds, okay? So this one now can connect to silicon again, then more 3. So it goes on like that. Silicon must have 4 around it. So it goes on again, silicon here, 1, then 2, then 3. You see that? The same thing continues. Yeah, so it has that giant structure. But then this one here, it has a simple molecular structure. Simple molecular structure. See, I mean, sulfur has how many bonds, how many electrons in the outermost? There are 6. So this is 1, 2, then 3, 4 shared. Then there is a lone pair here of electrons. So that is why you see that this one is bent. It is not linear. Okay. So this one is true because this one has a simple structure and this one has a giant structure, giant covalent structure. So ammonia has a high boiling point than phosphine. When you look at ammonia, on the nitrogen, we see a lone pair of electrons, okay? Now, this lone pair of electrons can be donated, but again, we also have what we call hydrogen bonding in here. So hydrogen can connect with another nitrogen here, which has a lone pair. So it can continue like that, okay? We have 3 elements that form hydrogen bonding. We have oxygen, nitrogen, and fluorine. Okay, so long as they have the hydrogens attached to them, then they can form the hydrogen bonds. And hydrogen bonding is very, very strong. Okay, hydrogen bond is very strong. And remember, when we are boiling, we have to break all of these forces. Okay, then phosphine doesn't have what? It also has the same structure. They are in the same group, so 5 electrons in the outermost. But this one doesn't form what? Hydrogen bonding. It's not amongst these 3. So even this one is correct. Now they are saying which statements are correct. Then I have to look for 1 and 2. So both 1 and 2. That is A. And then question number 2. How many neutrons are contained in an atom of iron with a mass number of 60? We know that iron is in position 26. So if this is 60 here, then number of neutrons will be equal to 60 minus the 26, which actually gives us 34. And the answer has to be what? C. Then question 3, the diagram shows a Boltzmann's distribution of molecular energies for a gaseous reaction at different temperatures and at 2 different activation energies. Then they are saying which combination of temperature and activation energy will give the highest reaction rate. Now, first of all, to give the highest reaction rate, you must have this experiment done under high temperature. And under high temperature, the average molecules, the molecules with average energy will reduce, okay? Because many molecules have gained kinetic energy. So those with that average smaller energy are going to reduce. They will now go to the other side, to the right, okay? I've always explained this one using the pass marks in class. You find that maybe the pass mark is what? 70%. And maybe there are 2 students that have gotten that. And maybe the teacher want to stream the class. So, but there are many people in 60, so they will say, okay, let us lower the what? The pass mark. So there have been very many people here. Now, since they have lowered the pass mark, okay, now you find that many of these ones are now going to cross this side. So you are having, all of these ones are having 60, okay? We have the 60%, we have these with 50%, 40. So these ones here will now shift to this side, and these people who were very many are now going to reduce. You see that? So that is why we see that this one goes to the right and this peak goes down. Do you see that? This peak goes down because the molecules have reduced in number that have gotten that small average what? Energy. Okay, so we have to look at T2. And then for activation energy, if you want a highest reaction rate, you have to put a catalyst. So when you put a catalyst is that substance that is going to increase the rate of a reaction rate, but by providing a pathway with the lower activation energy. So when you look at this Z2, you choose the lower activation energy, this one here. So we have to choose EA1, and therefore our option has to be a D here, T2 and EA1. Question: for the reaction between sulfur dioxide and oxygen has this equation. It is here, and we can see that it is an exothermic reaction. The forward reaction is exothermic. 1 mole of sulfur dioxide and 1 mole of oxygen are placed in a closed container and heated to a constant temperature. At this temperature, 0.8 moles of sulfur trioxide are present in the equilibrium mixture. Which statement is correct? Now, I can see in here they are saying the equilibrium partial pressure of sulfur dioxide is greater than that of oxygen. Then there is Kp. Then at lower temperature, the equilibrium amount of sulfur trioxide is lower than 0.8. Then there is the mole fraction of sulfur trioxide. Now, let's begin and see what happens. Now, we are going to have this reaction here, sulfur dioxide, then plus the oxygen, and then we get what? Sulfur trioxide. This one is done in the contact process when we are producing what? Sulfuric acid. Now, initially, at 2 is equal to 0, we have 1 mole here, then 1 mole here of oxygen, then we have nothing for sulfur trioxide. Are we there? Then at equilibrium, there is something that reacts off from here. It is an X. Are we there? But it comes this side. When you look at the mole ratio, there is 1 here, but this one is 2. That means what reacts off here comes this side here and becomes twice of it. Are we there? So here we also have 1, then minus, it will be X. Okay, 1 minus what? X here. And actually this one will be 1 minus twice X. Why am I putting twice X? It's because here the mole ratio is 2 to 2. I mean, yes, 2 to 2. So it's like 1, 1. So if what reacted off here is 1, in other words, for any reaction here, 2 moles of this react and 1 mole here reacts. So 1 and then the 2. As simple as that. Now, this one here, they said is 0.8. So 2x here, you equate it to 0.8. Remember at equilibrium, they told us this one here. That means x is going to be 0.4. Okay, 0.4. Then 1 minus 0.4, this one will be 0.6. And then 1 minus 0.8, we shall have 0.2. Now, Kp has these units. No, here when we are looking at Kp, it is going to be the partial pressure, and pressure can be in terms of pascals or Newton per meter squared, millimeters of mercury, and maybe atmospheres. You see that? So we don't use concentrations. That will be for Kc. You see? So this one I will actually take it out right away. Now, they said that the equilibrium partial pressure of this one is greater than this one for oxygen. Now, the fact that the moles of sulfur dioxide here are less than the moles of oxygen, there is no way sulfur dioxide here is going to have a partial pressure greater than that of oxygen. You see that? Because pressure will be directly proportional to the number of moles that are in there. You get that? Because we have PV. If PV is equal to nRT, you can see that pressure is directly proportional to the number of what? Moles present. So this one has to be off. Even when we are trying to find the partial pressure of oxygen, is going to be 0.6, then divide by the total number of moles. We have 0.2 at equilibrium, then 0.6, then plus this will be 0.8 for sulfur trioxide, 0.8, then times the total pressure. Now this one is going to be 0.6, then out of this will be 10, and then the 6. So, okay, that will be now 1.6. You see that? Times the partial pressure. I mean the total pressure. But then when you go to the one of what? Of sulfur dioxide, this one will be 0.2. Yes, 0.2, then divide by the 1.6. Automatically, this one here is going to be smaller than this, okay? So that's why I'm also keeping this one off. Then, what else do we have? They have told us that at a lower temperature, the equilibrium amount of sulfur trioxide is lower than 0.8. Now, at a lower temperature, that means you're going to favor this reaction here is exothermic. The forward reaction is exothermic. So that means when you lower the temperature, you are going to favor the forward reaction. Also, so since you favor the forward reaction, that means that you are going to get more of this sulfur trioxide. The yield is going to be to increase. So you are going to get more than the 0.8 that you are having here at equilibrium. You see that? So even this one has to be off. That means our only option left is D. You see that? And D, they are saying that the mole fraction of sulfur trioxide is less than 0.8. Let's look at the mole fraction of sulfur trioxide. Now, this one is going to be 0.8 because these are the moles at what? Equilibrium. Then divide by the total. We saw it is 1.6. This one will be a half, and a half is 0.5. This 0.5 is less than what? The 0.8. So it is correct. That means our answer is what? D. Question 5. Red lead is a red pigment with the formula, this one here. Every formula unit in red lead is the same. Each formula yield contains 3 lead ions and 4 oxide ions. Lead has 2 different oxidation states in red lead. Now, the ones that we know that are so common in lead is the +2 and the +4, okay? But then, just like this one here, for rust, we have lead, iron 3 tetraoxide, triiron. We said triiron tetraoxide. This one here. This one is coming from iron 2 and then iron 3. You see? These two, when you add them, they give you that. So that means when I look at lead 3, lead here with 3 ions and then we have 4 oxide ions. This one should come from lead 2. So I can have lead 2 oxide and then lead 4 oxide. It has to be like that. But oxygens are 4. That means if I put a 2 here, I'll get 2 oxygens and then 2 oxygens here to make it a 4. Okay, and then 2 leads and then 1 here, so they become 3. So that means we have 2 lead 2 oxides and then we have 1 lead 4 oxide in there. So we have this one is the +2 and then this one is what? It's a +4. So our answer has to be C. Question 6, some standard enthalpy of combustion data are given. These are the ones that are given here, and then they are saying using this data, what is the enthalpy change of formation of methanol? Now, here we are seeing enthalpy of combustion. Enthalpy of combustion, we are looking at 1 mole of a substance which is completely burnt in air. You see that? So we are having methanol. Methanol here is a liquid, then is completely burnt in oxygen. We shall get carbon dioxide and water. You see that? Then you have carbon dioxide, and then this one here, and also water. They come from carbon, the solid, then plus hydrogen, which is a gas, but then there is also what? Oxygen here. Because for enthalpy of formation, we are looking at forming 1 mole of a compound being formed from its elements in their standard states, standard conditions. Okay, so that is what we are having. This is the enthalpy of formation of this one here. If I can balance, we can see hydrogens are 4 there. I'll put a 2 here. Okay, even a 2 here to balance here. Then oxygens, what do we have? This is 3. This way we are seeing 4 oxygens. So if we are seeing 4 oxygens, I'll put 3 over 2 so that I get 3 here, then plus the one that is here. Okay, then the same thing I'll also do here. Now actually here I'll put a 2 such that it becomes a 4, just like here. Then from here, I'm having enthalpy of formation of this one here. So I'll put X here. Okay, it is the one that I'm looking for. And then here, the enthalpy of combustion of methanol is negative 726. So here we have negative 726. Okay, then we have enthalpy of formation. This one can be formation of carbon dioxide because it is from its element, but we can also have it as enthalpy of combustion of carbon. Okay, so enthalpy of combustion of carbon is this one here, negative 394. You see that? And then enthalpy of combustion of hydrogen, okay, it is going to be negative 286, but I will multiply this one by 2 because I'm burning 2 moles of hydrogen here. You see that? Now, using Hess's law, I can go like that. So I have X then plus negative 726. Then this one is equal to, these ones are going anti-clockwise. So clockwise is equal to anti-clockwise. As simple as that. Then we shall have negative 394, then plus twice of negative 286. So meaning for me to get X, I will take this one the other side. So negative 394, then plus 2 times negative 286. Then when this one goes this other side, it becomes a positive. So 726. Now putting this one in the calculator, what do we get? Negative 394 plus 2 into negative 286, then plus 726. We get negative 240 kilojoules per mole, and that is option A. Then question 7, which row is correct? The smallest bond angle and then largest bond angle. So we are seeing 3 molecules here, water, then ammonia, and then boron trifluoride. Now, what happens here? We are going to use valence shell electron pair repulsion theory. We look at the shapes of these molecules and then we look at the bond angles. Water, we have oxygen here and then the hydrogens. So this one is bent shaped because it has 2 lone pairs in there. And for these 2 lone pairs, we have the repulsion between them is stronger than the repulsion between. In other words, we can say the lone pair repulsion is stronger than lone pair bond pair repulsion, which is also stronger than bond pair repulsion. So because of that, first of all, these are 4. We consider like the 4 bonds, just like we can have this one for the tetrahedral, for let's say methane. Okay, for this one the angle is 109.5. Now when we replace this bond angle with a lone pair. Now for example, this ammonia here has a lone pair here, then we have hydrogen and hydrogen here. Now the repulsion between the lone pair and the bond pair is stronger than between the bond pair. You see that? So we expect now that angle to be smaller. This angle here, I mean between these bond pairs here, it has to be smaller than this 109.5, because something strong here is present. So it tends to squeeze these ones here towards themselves. So we are going to have now this angle probably coming to 107. Okay, smaller than what? 109.5. Now again, when I remove one bond angle and then I replace it with a lone pair, just like in water here, again we are going to have now the strongest repulsion in between the lone pairs, which is in turn stronger than the lone pair bond pair, and then stronger than bond pair. So that means this angle here is actually going to be smaller than this one here. So we can put it maybe at 105. And we always say 104 to 105. It has to be smaller than this one. You see? Let me take the 105. Then boron trifluoride, this one is trigonal planar. So we have this one here, and the angle in here is just 120. Okay, this one we call it trigonal pyramidal. Then this one we call it bent shaped or angular, or we say nonlinear. Okay, so from the smallest is for water, then followed by that one of ammonia, and then boron trifluoride. Actually, that is option A. As simple as that. Question 8. In the Haber process, that is the production of ammonia from nitrogen and hydrogen, the reaction between the two gaseous reactants requires the use of a catalyst that contains a transition element. Actually, that is iron. That means I have to look at these two here. What is the metal, and in which mole ratio do these gases react? Now, remember, I said it has to be iron here. Now we have nitrogen reacting with hydrogen, then we get 2 moles of ammonia here, 2 here because nitrogen here is 2, okay, and then hydrogen here is 2 times 3, that one becomes a 6, so I will put a 3 here, okay, and then the DH here is a negative, I think 92 kilojoules per mole, something like that. Then the mole ratio is 1 to 3. You can see that 1 to 3. So which is here? That means our answer has to be a B. And then question 9. Aqueous hydrogen peroxide decomposes into water and oxygen in the presence of a suitable catalyst. Okay, and that one is it vanadium pentaoxide? Something like that. Then 50 cubic centimeters of 0.5 molar solution of hydrogen peroxide produced 120 cubic centimeters of oxygen in 2 minutes. The volume of the gas was measured at room conditions. What is the average rate of decomposition of hydrogen peroxide during this 2-minute period? Now what we are going to do first, we write the equation. So we have hydrogen peroxide here, which is a liquid, actually decomposes into water. Okay, then that water is a liquid, and then oxygen here, which is a gas. So to balance this equation, I can put a 2 here, so that oxygen becomes 2, then plus the 2, that is 4, then I can put a 2 here. You see, hydrogen is 4, hydrogen is 4, oxygen is 4, oxygen is 4. All right. Now you must put a balanced equation, because when you fail to put a balanced equation, then, and remember here in mole concept, you have to use the stoichiometry. Okay. Now, we need to look at moles of oxygen. Moles of oxygen here, it is 120. 1 mole of a gas at room temperature and pressure occupies 24 liters or 24,000 cubic centimeters. So we get this one that is gotten, and then we look at 24,000. We divide it by 24,000. How does this one come about? You can say 24,000 cubic centimeters of solution contain 1 mole of a gas. Then how about the 120? So you have the 120 times 1, then divide by this. So that is how we come to divide. Okay, so that is that. 120 divide by 24000. This one gives us 0.005. 0.005 moles of oxygen. Then moles of the peroxide that reacted. Now here we use the stoichiometry of the reaction. So this is 2 to 1. That means we shall multiply what we have gotten here by what? By 2. And this will be 0.01. Okay. Now the total number of moles in here, we shall get this 50 divided by 1,000, then times this. But now these are the ones that have reacted off, but they are coming from this volume of 50 cubic centimeters. So we shall say 50 cubic centimeters of solution, okay, contain the 0.01 moles of the peroxide. You see that? Then how about 1,000 cubic centimeters? So we need to see the concentration that reacted off the what? The 0.5 molar. So this one here will contain it's 1,000 times the 0.01, then we divide by 50. What do we get? 1,000 times 0.01, we divide by 50. This one is 0.2. So this is 0.2 moles per liter. So now the rate is going to be that concentration that has reacted off. Okay, because rate, we look at the how the reactant decomposes. So what has reacted off? What has reacted is this 0.2. Okay, moles per liter. Then we are dividing by time, but since when you look at all of these units, it is in per second, so we are dividing by time. Rate, you look at the concentration, then divide by the time, and the time that we are having here is 2 minutes, but in seconds it has to be times 60 here. Okay, so when we put this one in the calculator, what do we get? 0.2 divided by 2 times 60. This one gives us 1/600, which is 0.0016 recurring. Okay, 0.0016666 is recurring. That means to 3 when you look at whatever we are having here, we have 2 significant figures, then we shall round this to this, and it will give us 0.0017. That means our answer is going to be a C there. Then question 10, the average intermolecular forces in water are much stronger than the average intermolecular forces in steam. Water is a liquid. Okay, that means the forces in there, yes, are stronger than when you look at the ones in the gas, because in the gas all the forces have been completely broken down. Okay, then the average intermolecular forces in ice, now that one is a solid, are slightly stronger than the average intermolecular forces in water. That is also true. Enthalpy changes are associated with the equilibrium processes shown. Okay, these are the ones here. This is the enthalpy for boiling. Okay, you are moving from the liquid to the gas. Then the enthalpy change for melting here, you are moving from the solid to the liquid. Now you are breaking bonds here. Okay, you are breaking intermolecular forces between the water molecules. That means this one has to be exothermic because you are putting in energy. Then also here, you are breaking the intermolecular forces in the solid. You are trying to weaken them. You go to the liquid. Then even here, you are putting in energy. So it is positive. Then they are saying which statements are correct. This and this are both negative. No, we have already seen that they are what? Positive. That means wherever there is one, I just cancel. There is a 1 here, there is a 1 here, there is a 1 here. Don't you think the answer is D? But let's look at D. The enthalpy change for the boiling is greater than the enthalpy change for melting. Yes, for melting, you are just weakening the forces in there, and hydrogen bonding is still there for the water molecules. You see that? But then when you come to the gas, you have completely broken all the intermolecular forces. You get that? So in there, we are going to find that the one for moving from the liquid to the gas, it is going to be greater than the one for melting. Okay, so this one is correct. Then the intermolecular forces in ice and water are of the same type. What do we mean that they are of the same type? We have the hydrogen bonding in there, okay, and then the covalent bonds. So they are the same type. That's why 2 and 3 are correct.